Hi, and welcome to the final chapter in this four-part tutorial on how to build a working 3D virtual prototype using Capext. In the previous sections, we tested the PCB for a capacitive touch remote control by first building a virtual prototype with simple, flat plastic overlays. Based on the test results, we did some modifications to the PCB and then assembled a 3D prototype that accurately represents the final design. Now the time has come to test our 3D virtual prototype and see if it performs as expected. We test this prototype the exact same way we tested the board with the flat overlays. First, we enable the touch probe. Then we select Area Touch. Since the 3D body extends a bit outside the PCB, we will extend the touch area a bit to make sure we get full coverage. We then select all the X electrodes and start the simulation. The simulations of all 5 X electrodes, including the grip sensor, took about 2 minutes. Let's check the grip sensor first. We see that the grip sensor has a good touch response on the underside of the remote, which is expected since the electrodes sit on this side of the board. You observe that there is also some response on the overside, but this is of no concern since the purpose of the sensor is to wake the device up when grabbed by hand. For the trackpad, we want to look for consistency first. So we select the sensor and lock the scaling by selecting Use Custom Scaling. This prevents the color scale from recalibrating for each sensor we inspect. Moving through the matrix reveals that the touch response is stronger towards the edges, except at the very edge. This is because the Y electrodes are of half the area here. The weaker touch response in the center is expected because there is just more plastic between the touch surface and the electrodes in this location. This all has to be compensated for in software to ensure linear interpolation. Without linear interpolation, the software will be unable to calculate the exact position of the finger. Here, the results from Capext are extremely valuable as the strength of the touch response can be read out directly. Those values are used to calculate the scaling that needs to be applied to the touch readings in software before they are input to the interpolation algorithm. In tutorial 2, at timestamp 1343, we decided that an unintended touch response would be left since the air gap above it would weaken the response from the outer surface. That judgment turned out to be a good one. That particular spot, X1 and Y6, does not show any unintended touches in the same area. If we flip the remote around and look at the underside, we see something of a concern to us. The trackpad has some weak touch responses on the underside of the body. If you imagine how one would hold the product while operating the trackpad with one's thumb, this part would rest on the index finger of the hand, which then could interfere with the interpolation and thus cause the software to calculate the wrong finger position. So how do we prevent the trackpad sensor from registering touches from the underside? One method that is guaranteed to work is inserting a metal shield. From a production standpoint, this is both complicated and expensive, so we are only doing this to demonstrate the capabilities of Capext. Here we have created a thin object underneath the trackpad. Let's swap out the existing 3D model with this one and make this object into a metallic shield. But first, let's save the design under a new name in order to keep the old design for comparison. Clicking the file name of the parent submodel brings up a menu for loading a replacement essenstial model. This model will replace the existing one, but assume the same orientation, location, and scaling. Here we see that the model has imported correctly. Now we need to reassign all materials properties. Everything is plastic except for the shield and the battery, which are both metal. We first assign the body as plastic and let all submodels inherit this property. Then we identify the battery and the shield, rename them, and assign their materials properties as metallic. We then reselect this box to collapse the list and make the list more viewable. The two metallic submodels remain metallic. A cross-section view confirms that the PCB is surrounded by plastic with a metal shield in the correct position. Let's start the simulation, and while that is progressing, start a second instance of Capext so we can evaluate the model without the shield side by side with this one. And here are both designs neatly arranged side by side, the original design to the left and the design with the shield to the right. We can clearly see that all the shadow touches on the other side have disappeared. Now, as mentioned, the metal shield is an expensive and impractical way to get rid of the unwanted shadow touches. Remember how the weak, unintended touches near the MCU almost completely disappeared when we got some air between the PCB and the touch surface. We can use that same effect to our advantage here as well. By adding an air-filled cavity underneath the trackpad, the electric field should be sufficiently muted that we'll see those shadow touches disappear. So here is our remote body with that cavity added. And what concerns the shadow touches, let's compare without and with the air-filled cavity side by side. Just a very weak signal remaining. So weak it will not interfere with the trackpad interpolation. A side benefit from the air cavity is both that default capacitance between electrodes and touch delta are 10 to 20% stronger. The discontinuity in permittivity directly under the trackpad pushes more field lines up to the upper surface of the plastic body. So that marks the end of a successful design. A real prototype of this remote control is expected to work just as well as our virtual prototype. However, there is one last thing I want to do. Go back and load the previous PCB into the model. We had some long streaks of unintended touch that are not expected to have disappeared since that part of the board is still covered in plastic. However, there was one heavy via-induced touch near the MCU that we decided to remove with a ground plane. Was that really necessary, given that we have a substantial air gap above that part of the board? Well, apparently it was. The air gap above the components has weakened this unintended touch quite a bit, but not sufficiently that it would not have caused problems if left unattended. We are going to end it here with a final summary of our estimated time difference between this way of evaluating a 3D design and the traditional way. Your results may vary, but it is not unreasonable to conclude that we shorten this part of the design cycle from over a month to a couple of days. If you think this was useful, head over to capext.com to start your free trial today. Thanks for watching.